Hello everyone, my name is Dailisa Ronda Perez. I'm currently pursuing my PhD degree in the Institute of Smart System Technology at Klagenfurt University. On this occasion, I will be presenting the results on the paper titled High Accuracy Reconstruction of Periodic Signals Based on Compressive Sensing. Nowadays, many applications are in favor of wireless smart transducer, which have a limited power budget. This need to minimize energy consumption in the sensor node has led to the introduction of a more effective sampling strategy based on compressive sensing. This can potentially reduce the high impact of sampling rate on the overall power consumption of systems dealing with sparse signals. We are especially interested in autarkic sensing applications dealing with periodic signals, which appear in many applications like vibration monitoring, for example, where the signal's frequency is typically in the order of kilohertz, but when we want to employ energy harvesting, keeping the sensing system small, it is not possible to afford such high sampling frequencies. And on the other hand, the estimation accuracy of vibrating signal parameters is essential to correctly identify structural defects before the system reaches a critical state. This is why in this paper we propose a two-stages optimization approach to improve the estimation accuracy of periodic signals. In a nutshell, compressive sensing is a novel signal image acquisition technique that enables efficient data sampling at a much lower rate than the requirements indicated by the Nyquist theorem. Typically, periodic signals can be expressed in terms of the fundamental frequency and harmonics as a superposition of k sinusoidal waveforms. The fundamental frequency is given by f1, and the frequencies from f2 to fk represent the harmonics that can be expressed as positive integer multiples of the fundamental frequency. Considering that the vector S is a finite length discrete representation of the signal, it has a kappa sparse representation in the discrete Fourier transform domain only when the sinusoids can be expressed as integer multiples of the frequency step size in the DFT basis. In the general case of non-integral frequencies, the discrete Fourier transform coefficients do not present the same sparsity properties due to the spectral leakage. One way to overcome this problem is to introduce a redundant DFT frame or dictionary that corresponds to a finer discretization of the Fourier representation. The DFT frame with redundancy factor P is defined by the matrix psi p containing np vectors, where each vector has elements of the form here expressed. Taking advantage of the sparsity property, a compressive sensing framework is employed where the signal is acquired by a reduced set of m linear measurements of the form here expressed. Y stands for the measurements vector, the matrix phi is the measurement matrix, and X is the sparse signal vector. The matrix A is referred as sensing matrix, and to guarantee robust sparse recovery from undersampled data, some properties should be fulfilled. The sensing matrix must obey the restricted isometry property, and maximal incoherence between the pairs phi and psi should be achieved. It has been already proven that both properties can be achieved with high probability by selecting phi as a random matrix, and several efficient recovery methods based on convex optimization or grid solutions are already available. Nevertheless, most of the state-of-the-art recovery techniques focus on the frequency estimation problem, but we are also interested in an accurate estimation of the amplitude and phase, which is why we present here a two-step reconstruction approach named Opti2. In the first stage, the well-known basis pursuit denoising algorithm is used, which solves the L1 regularized optimization problem to find an estimation of the sparse representation of the signal that is then used to find a first estimation of the signal S. The support of X, which is the set of indexes associated to its kappa non-zero coefficients, is used to find a first estimation of the frequencies, with the first frequency to corresponds to the fundamental frequency. The amplitudes and phases are estimated using the least square solutions, keeping the columns of the DFT frame of redundancy indexed by the support of X. We exploit the fact that the frequencies from F2 to Fk represent the harmonics of the fundamental frequency. Then we aim to refine the estimation of F1 and the parameters by solving a nonlinear optimization problem in an iterative fashion. In the second stage, we define a search space around the first estimation of the fundamental frequency F1 given by the interval I. Then I is split in J subintervals of width delta, and the nonlinear optimization problem is solved for each subinterval subject to these specified constraints. At the end, we keep the solution that give the minimum error, and the corresponding set of parameters is used to find a final estimation of the signal. The proposed approach, Opti2, is evaluated through a set of numerical experiments performed in MATLAB. The performance is measured in terms of the mean square error of the estimated signal via Monte Carlo experiments and averaged over 30 independent trials. The signal's parameters are generated uniformly at random at each experiment. An observation interval of 30 milliseconds and sampling frequency of 10 kHz are considered for the simulated data, with K equal to 4 sinusoidal waveforms, and the measurement matrix assumed to be Gaussian. The figure depicts the results of the first experiments, where a fixed number of 150 measurements and varying signal-to-noise ratio from -5 to 20 dB are considered. Here, Opti2 is compared with some of the state-of-the-art reconstruction approaches, and it can be noticed that Opti2 outperforms all of the evaluated approaches, reducing the mean square error of the estimated signal in the second optimization step. For the second experiment, the mean square error is evaluated in terms of the number of measurements, where a range of subsampling ratios is explored with noiseless measurements to verify the compression level that allows a successful estimation. The results here in the figure shows that Opti2 achieved the best performance, converging to a minimum mean square error with 20% of compression rate. The table here lists the average computation time of the evaluated approaches, considering a scenario with signal-to-noise ratio of 30 dB and 150 measurements. It should be taken into account that the computation time of Opti2 includes the delay of the first estimation step, showing that the second stage doesn't increase the computation time considerably. To conclude, in this paper, a two-stages reconstruction approach, referred as OPTI2, is proposed to improve the estimation of the periodic signals that can be expressed as a sum of real value sinusoids. The estimation provided by one of the well-established recovery techniques for compressed measurements is used as first estimation, which gets refined in the second stage by iteratively solving a nonlinear optimization problem. Experimental results show that OPTI2 outperforms reported techniques used in spectral compressive sensing, achieving accurate results in terms of the mean square error. Thank you very much for your attention.